Welcome to part 3 of this week's online lecture. In part 3 we will discuss the vibrational selection rules for harmonic oscillators and the effect these selection rules have on the vibrational spectrum. To determine the selection rules we will follow exactly the same approach as we did for the rotational system. We need to determine what the vibrational transition moment is. We'll have a vibrational transition if the vibrational transition moment is non-zero. Remember, this involved solving a nasty integral. I'll be illustrating that in just a little while. When we solve the integral, we are able to identify the selection rules. The first selection rule is the gross selection rule. This states that the gradient of the dipole moment with respect to the displacement at the equilibrium position must be non-zero. What does that mean? It means that the dipole moment must change with displacement at the equilibrium position. As the vibration goes through the equilibrium position, the dipole moment of the molecule must be changing. As we'll see, that does not mean that it has to have a permanent dipole moment. The second selection rule is the specific selection rule, and this is that delta V must be plus or minus 1. Therefore, I can go from V equals 0 to V equals 1, but I cannot go from V equals 0 to V equals 2. Similarly, I can go from V equals 1 to V equals 2, but not from V equals 1 to V equals 3. So we can only have transitions between adjacent vibrational levels. Now, where do these selection rules come from? Why was I able to say what the selection rules were? Note that the description I'm about to give is non-examinable. This explanation is being given so that you understand that the selection rules are rigorously determined and not plucked out of thin air. The thing that we notice about the dipole moment is that it changes with bond length. Remember, dipole moment is just charge times distance. So it is going to change as bond length changes during the vibration. We could expand the dipole moment around the equilibrium position as a function of the displacement. Essentially, expand it as a Taylor series, as we did with the potential before. And it will look like this. For this explanation, I can ignore all the higher order terms. I'm only interested in these two terms here. So I know that my dipole moment is a function of the displacement. I can substitute it into my calculation of my transition moment here. The mu e is the dipole moment at the equilibrium position, and so it is a constant, and so it can come out of the integral. How about this second term? When I substitute the second term into this integral, the gradient term here, which is the differential of the dipole moment with respect to displacement, is also a constant, so it can come out of the second integral. The displacement, however, cannot come out of the integral because the wave functions themselves depend on the displacement, and so of course this integral is also a function of the displacement. So what are the values of these terms? Well, if I'm going to get a transition, these have to be non-zero. The first term is 0. The mu e is of course the permanent dipole moment of the molecule. It could be 0 or it could be non-zero. It doesn't make any difference. This is because I know that this integral is 0. I'm not going to explain in any detail why, but these vibrational wave functions that are solutions to the harmonic oscillator Schrödinger equation are orthogonal to one another, and so integrals like these are always 0 if there is a change in the vibrational state. Then we've got this second term. So because the first term is 0, if I am going to see a vibrational transition, this second term better be non-zero, which basically means that both parts of this term have to be non-zero. This constant has to be non-zero, and this integral has to be non-zero. Well, this first part being non-zero is of course the gross selection rule. Solving the integral is where you get your specific selection rule, that delta V is equal to plus or minus 1. Well, this was non-examinable, but it is from solving the transition moment integral that we get our selection rules. They arise from some fundamental mathematics. The first selection rule is that the dipole moment as a function of the displacement has to change as we go through the equilibrium position. Of course, for homonuclear diatomics, this cannot occur. The dipole moment for a homonuclear diatomic is zero no matter what the bond length is. During vibration, its dipole moment stays zero and its gradient stays zero. So therefore, homonuclear diatomics cannot exhibit an infrared or vibrational spectrum. They are known as infrared inactive. And of course, this satisfies the first observation that we discussed at the very beginning of part 1. It does not mean that homonuclear diatomics do not have vibrational levels. It just means that I cannot use electromagnetic radiation to excite the molecule from one vibrational state to another. In just the same way, I cannot excite a homonuclear diatomic from one rotational state to another using microwave radiation. But the vibrational levels, of course, do exist. The Schrödinger equation tells us what the energies of those levels are. How does a molecule change from one vibrational level to another? Well, simply by bumping into another molecule. Thermal energy will change the vibrational state of the molecule. For a heteronuclear diatomic, the dipole moment is changing. So remember, the dipole moment is just charge times distance. As the bond length changes, the dipole moment changes. And for that reason, heteronuclear molecules do have infrared spectra and are known as infrared active molecules. This is essentially accounting for our second observation that carbon monoxide dissolved in a solvent has a vibrational band in the infrared. And so, we have explained the first two observations we made with regard to vibrational spectroscopy. What about a molecule that doesn't have a permanent dipole moment, but we know that it is infrared active? Something like carbon dioxide. We know that this molecule is infrared active. We know that this is the second most important greenhouse gas in our atmosphere. It is the reason why we are worried about the emissions of carbon dioxide, because the more carbon dioxide we put in our atmosphere, the higher the surface temperature. And that is what we are witnessing at this moment in terms of global warming. So we know it must be infrared active, but its symmetry seems a bit peculiar, because we might expect perhaps that this molecule won't have a dipole moment while it's vibrating. But there's of course more than one vibration that can occur in this molecule. During the symmetric stretch, as the oxygen atoms move out in phase with each other, the CO bond lengths stay the same, and the dipole moment is zero at every point during the vibration. And so that particular vibration of carbon dioxide is indeed infrared inactive. But when one CO bond is getting smaller, while the other CO bond is getting longer, in a so-called asymmetric stretch, then, in that case, the dipole moment is changing during the vibration. The dipole moment of the asymmetric stretch will look something like this. We define our displacement as a kind of vibrational coordinate, which is positive when one of the bonds stretch and is negative when this bond goes through compression. Then on one side, when the displacement is positive, the dipole moment will be positive, and of course at equilibrium the dipole moment is zero, but if the displacement is negative, the dipole moment is negative. If you look at the gradient of the dipole moment as you pass through the equilibrium position here, then you can see that the gradient is non-zero, and so therefore this asymmetric stretch does indeed absorb infrared radiation. We can excite vibrational transitions for asymmetric vibrations. We also have another vibration in this molecule, which is the bending motion. You can imagine that the OCO bond angle can change in a bending vibration. In such a vibration, the gradient is also non-zero, and so the bending vibration of carbon dioxide will exhibit an infrared spectrum. So the specific selection rule is that the vibrational quantum number can change by plus and minus 1. So let's look when the vibrational state changes from V to V plus 1. Let's calculate what the delta E is. Well, instead of the change in energy, let's calculate the frequency associated with the change in energy. And we can determine that by dividing the energy by Hc tilde. This will tell me the vibrational frequency of the associated spectral line. Well, this will just be equal to the vibrational term for V plus 1 minus the vibrational term for V. So we just substitute in for the vibrational terms of V plus 1 and V. You can see that the V plus a half is going to cancel and we'll just be left with nu 0. Thus, for the harmonic oscillator approximation, we expect that all transitions, say from V equals 0 to V equals 1, or from V equals 1 to V equals 2, will all exhibit a spectral feature at nu 0. Thus, all the spectral lines associated with every transition occur at exactly the same frequency. In the spectrum, they will all lie on top of one another, so in the spectrum we will only see a single spectral line. This is a lot simpler than the rotational spectrum, where we had lots and lots of equally spaced lines. In vibrational spectroscopy, we have just a single line. So far, we have discussed what is known as a harmonic oscillator. However, there is a problem. If we stretch a real molecule too much, it will get to a stage where it breaks. The molecule will dissociate. This basically means that the harmonic model approximation fails. And we know that because we've seen the real electronic potential energy and we know that it doesn't follow a harmonic potential. A real potential tends to zero as the bond length gets larger and larger. If we go beyond that level, the bond is broken. This is the end of part 3 of this week's online lecture. Please continue on to part 4.